Hello, boys and girls out there. It's been quite some time since I posted anything on the YouTube. This time around, instead of coming up with multiple choice questions, I am now trying to solve a few database questions to help you all answer the database questions in a much better way. As you all aware, from this year on, the database questions will be asked as a part of paper 1 itself. Whether you take physics at a higher level or at a standard level, database questions is one of the part of your paper 1. So here we have a particular question with regards to some data. You need to understand that whenever we are talking about a database question, it has nothing at all to do with whether you have done that particular concept or not. In this particular question, if you notice, there is a standing wave that has been established, and the first harmonic of the standing wave has been established. Now, whether or not you have done this concept, that is immaterial. You will just have to follow the instructions and the information that has been given to you. The name itself indicates this is a data-based question. Alright, so let's try to understand what this question is about. A student attaches one end of a copper wire to an oscillator operating at a fixed frequency, indicating that frequency here is a controlled variable. The other end of the wire, it says, passes over a pulley to weights that hang vertically. Alright, the first harmonic standing wave is established by using the slider to change the length of the wire. So this length of the wire that is hanging, that is being changed, that is being altered by changing the position of this particular slider over there. Alright, the procedure is repeated for different weights, indicating that the weights here, that becomes your independent variable, and automatically the length of the wire becomes your dependent variable. He further goes on to say that the mass of the weights m and the wavelength lambda of the wave are related by this particular equation. Now, if you notice carefully, the length of the wire is actually the dependent variable, but in this equation there is nothing related to length of the wire. We need to understand that based on the length of the wire, the value of wavelength here is changing. Alright, so he continues to say that this is the formula which relates the mass of the weights that are hanging down there and the wavelength of the wave that has been established in this particular stretch or length of the wire. Goes on to say that mu is a constant. We are unaware as to what this mu is. F anyways is the frequency, which is a fixed frequency control variable. G is acceleration due to gravity, and its value has been given to us here. It is 9.8 meter per second squared. Alright, it goes on to say deduce the unit of mu in terms of the fundamental SI units. Now, very often the question could actually be a bit misleading. We need to differentiate between the SI unit and the fundamental SI unit. Now let me try to differentiate between the two of them. If you look at the unit of force, the SI unit of force is Newton, but the fundamental SI unit of force is not Newton. It needs to be expressed in terms of the fundamental physical quantities. So in this case, the fundamental SI unit for force, we pretty well know the formula for force is actually F is equal to m into A. M here is the mass, so that will be kg, and acceleration will be meter per second squared. So the SI unit of force is Newton, while the fundamental SI unit would be kg meter per second square. Whenever you answer a question based on deducing the unit of a particular physical quantity which you are unaware of, please try to pay some extra attention to what is being asked. Is it the SI unit or is it the fundamental SI unit? Alright, so in this particular question, it says that, hey, you know what, determine the fundamental SI units of mu. So I would go ahead and make mu as my subject here, which will then give me m into g upon f square lambda square. The SI unit of m, mass, is kg. G is acceleration due to gravity, therefore that will be meter per second square. Frequency, the SI unit of frequency here, we need to understand it is a hertz, which can also be written as per second. Here it is frequency squared, so I would prefer writing that as per second square. And then finally lambda square. Lambda is measured in meters, so that will be meter square. Now as you can observe here, I can obviously strike off per second square and second square. 1 meter goes off with 1 meter, therefore I am now left with kg per meter. So the fundamental SI unit of mu is going to be kg per meter. It further goes on to say that the graph shows the data obtained by the student plotted to show the variation of m with lambda square. Alright, now let us rewrite the equation that has been provided to us. The equation that has been provided to us here is m is equal to mu times f square upon g into lambda square. Alright, if you observe this carefully, this is in the format of y is equal to mx plus c. The only thing that he has not mentioned obviously here is plus 0. Now, the equation that has been provided to us is representing the equation for a straight line, which further goes on to say that if at all I plot mass along the y-axis, which is what has been done here, and lambda square along the x-axis, which is again what has been done here, the gradient of this particular slope would be mu times f square upon g, and the y-intercept should have been 0. Alright, so this is the analysis that you should have already been ready with even before proceeding further with the next set of questions. Right, so it says draw the line of best fit for these data. From this particular analysis, it is quite obvious that the set of data that we obtained should have been a straight line of best fit, and that is what I will try to plot here. Now when I try to draw this line of best fit, it's very confusing, you know, how should this line of best fit pass through, where should it pass through, and all. As of now, if you notice, this cannot be considered as a line of best fit because this particular line is not passing through all the data points. Now, do you think it is remotely possible for us to let it pass through each and every data point? Let's check this out. So this is what I have done. I noticed that, hey, you know what, this line of best fit is actually not passing through all the data points. So how do I do this? The logic that I generally follow is, I would always try to connect the first data point and the last data point. That will be my primary objective. Once I do that, I then check if this particular line of best fit is passing through all the error bars or not. If not through all the data points, it should at least pass through each and every error bar. And I noticed that this particular line of best fit is actually passing through each and every error bar. Moreover, whenever you plot the line of best fit, you again need to pay very close attention. The line of best fit need not always be a straight line of best fit. Sometimes the line of best fit could also be a curve. Look out for this particular series of questions. I shall be posting more questions with regards to a line of best fit which is not a straight line but indeed a curve. So do have a look out for this. In this particular scenario, I decided to plot a straight line of best fit. Quite obvious, because the equation that has been provided to me is representing a straight line of best fit. Moreover, the other thing that you need to bear in mind while drawing your line of best fit is that please ensure that your line of best fit intersects either the x-axis or the y-axis as may deem fit. In this particular scenario, there is no point in further extending this to intersect the y-axis because the further axis is not shown to us. However, we can clearly notice that it is intersecting the x-axis at a specific value. It is certainly not passing through the origin. So please be mindful about that. Right. The next question is identify the evidence for a systematic error in the data. Now, whenever we talk about systematic errors, again, fall back onto the equation and fall back onto the line of best fit that has been drawn. In accordance with this equation, the expectation is that the y-intercept value should be equal to 0. However, in this particular scenario, it is not equal to 0. That is an indicator enough that there is a systematic error. Now, is there any other methodology as well to identify whether there is a systematic error or not? Well, the answer is, of course, a yes. The gradient here should have been mu times f square upon g. In some scenarios, this particular gradient should be, representing a very specific value. Though in this particular question, the value of the gradient has not been provided to us, but in some scenarios, in some questions, the value of the gradient will be provided to us. Now, if the value of the gradient has come out to be some other value other than what it should have been, that again is an indicator that there is a systematic error. So there are two different methodologies or two different mechanisms through which we can identify the presence of a systematic error. One is the y-intercept value and the other will be the value of the gradient. So be mindful about this. In this particular scenario, the evidence for the presence of a systematic error in the data is that the line of best fit is not passing through the origin. That is what you will have to specify here. Now, if there is a systematic error, what could have been the reason behind this? And that is what the next question is. Suggest a possible reason for the systematic error. Now, as I mentioned earlier, it is not necessary that you need to have knowledge of the particular experiment, or it is not necessary for you to actually conduct the experiment at school. Kindly go through what all information that has been provided to you. The reason for the presence of systematic error might lie hidden somewhere over there. In this particular scenario, let's try to understand this. It says that the student attaches one end of a copper wire to an oscillator operating at a fixed frequency. Wonderful. The other end of the wire passes over a pulley to weights that hang vertically. All right. Now, it has never been mentioned whether the friction around this particular pulley system is being considered or not in the overall force acting on the wire. That could be one reason behind the presence of systematic error. All right. It goes on to say that first harmonic is established, changing the length of the wire. All right, length of the wire has been changed. What is the instrument? What is the measuring instrument that has been used to measure the length of the wire, based on which the value of a wavelength is being determined? So probably there could be a zero offset error or a zero error. Probably the person is not reading right from the zero of the scale, or probably there is no zero present in the first place. That could be the source of another systematic error. The procedure is repeated for different weights. All right. So the weights here are changing, but it has never been specified to us whether the weight of the tray in which the weights are being kept, whether that has been considered or not. That has never been specified here. So that could be the presence of another systematic error. So there are three major errors that we have identified which could contribute towards systematic error. One is friction across the pulley system. The second could probably be the the weight of the tray itself, which has not been considered. And the third possibility could be the usage of the ruler that is being used, to measure the length, and probably the zero error of that probably might not have been considered. For all that it takes, the weight also may be measured properly or not. So that could be another possibility for the presence of a systematic error. Further goes on to say, okay, calculate the gradient of the graph. A very common mistake that the students would be making while calculating the gradient of the graph would be, they will consider, all right, so gradient is equal to y upon x, and they will consider one single data point and they will try to determine the gradient. That is a classic mistake. Never ever do that. The gradient is always determined using delta y upon delta x. Delta y upon delta x clearly indicates that we will have to consider two data points at least to determine the gradient. Now these two data points, am I allowed to consider, say, the data point here and the data point here? Am I allowed to consider these two data points? No, try to avoid that mistake. The reason that it is a mistake is because there are two reasons specifically here. Reason number one, these two data points that I marked are pretty close to each other. Therefore, try to avoid them. Do not consider two data points which are very close to each other. Try to consider two data points which are as far away from each other as possible. That is the first pointer that we need to bear in mind while determining the gradient. The second point that we need to consider is that I cannot consider this data point in the first place at all. What could be the reason behind that? If you notice, this is our line of best fit. The data point here, though it is an experimentally determined data point, this point is not lying on the line of best fit. So avoid that, which goes on to say, consider two data points which are actually lying on the line of best fit. They need not necessarily be the experimental data points that have been provided to us. So be extremely mindful about that. So in this particular scenario, instead of considering these two data points, I would rather consider this data point itself here and the final data point over there. So how would I now determine the gradient? The data point here would be around, so this is 1, 2, 3, 4, 5, 6, 7, 8. So 8.5. 8 will be 0.16, 0.17. 0.17, and this one here would be around over there, 1, 2, 3, 4, 5, 6. So that will be the sixth point, indicating that will be 30. All right, and then the second data point here, it would be right over there. This one will be 0.8, 0.81, 0.81. All right, and the data point here would be 150, 1, 2, 3, 4, 5. So that will be 175. 175 minus 130. Let's try to do this calculation. 175 minus 30 divided by 0.81 minus 0.17. The value comes out to be 226.5625. Therefore, the gradient here can be written as 226.5625. never ever forget to write the units as well. Mentioning the units is extremely important. Here in this case, delta Y is being represented with a change in mass, therefore grams, and delta X is being represented with lambda square, so gram per meter square. Again, we need to understand, whenever you are reporting the final value, try to always express it in the SI unit system. In accordance with the SI unit system, this will therefore be 0.2265 kg per meter square. So that will be the answer for which question here? Calculate the gradient of the graph. All right. It goes on to say the percentage uncertainty of the gradient is 6%. All right, 6% is the uncertainty in the gradient. Frequency f of the wave is this much. Remember, he mentioned that the frequency is a fixed frequency. All right, estimate using the answer to B4. B4 is in fact the gradient itself, so we will have to make use of this particular value to determine the mu for the string. All right, so how do we do this? We determine the gradient. Remember how we analyzed this stuff earlier itself. The gradient here represents mu f square upon g. So that is what I shall consider gradient. Gradient is equal to mu f square upon g. From this, if I make mu as my subject, mu is equal to gradient times g upon f square. All right, so gradient value is 0.2265. The value of a g, we have been advised to consider the value of g as 9.8 divided by 60, so that will be 60 square. The value therefore will be 0.2265 into 9.8 divided by 60 squared, comes out to be 6.165. 6.165 into 10 to the power negative 4. 10 to the power negative 4. Again, as I mentioned earlier, important to specify the unit. We already determined the fundamental SI unit of mu in the very first question, so we need not do the entire exercise again. It is a kg per meter. This one here is kg per meter. But then if you notice the question, I mean, it's a very general mistake again, oversight. The moment the value of mu is obtained, students generally tend to stop their answer over there. But then the question says, include the percentage uncertainty of a mu in your answer. Now, if you notice, a mu here involves, the calculation of mu involves multiplication and division. Whenever there is multiplication and division involved, we always add the corresponding percentage uncertainties. The percentage uncertainty in the gradient has been given to us as 6%, and the percentage uncertainty in the value of a frequency has been given to us as a 2%, but then there is frequency squared, so that will be 2 times a 2. Therefore, the overall will be 10%. Therefore, mu value is now reported as 6.165, 10 to the power negative 4, 10 to the power negative 4, plus or minus 10% unit kg per meter. There you go. This is the entire solution for the first database question. Have a look out on this particular section for understanding how to solve more database questions. Goodbye.